So, hello, and welcome everybody. Our sincere apologies for the technical glitch we faced, but thankfully it is sorted out. And I just like to let you know that people who have joined online, thank you for joining us. And I'm welcoming you sitting in New Delhi at IIT Delhi, Indian Institute of Technology, Delhi, along with my colleagues and consortium partners from EDITS project and EDITS network. Uh, just to let you know, we have also joined by some of the Indian think tankers, expert, and policymakers here in the room. So, what we will be presenting and sharing in front of you are actually modeling exercises, different modeling exercises, which we did under EDITS India First Track project. Uh, just quickly, as we already know, the brief introduction for EDITS project is basically uh, EDITS EDITS is a project a network precisely, which is Ministry of Economic coordinated by IIASA, which I mentioned. And under this network, we are now analyzing whether a high level of well-being can be achieved with a low energy demand scenario, what we call high with low scenario in global south countries. And for this, we have received a funding from METI and Wright, and this is what the work we are going to share in front of you. First question is, as you may have seen that this is about Indian case study. So some of you may raise the question, why India in the global south? So for that, what we need to understand that globally, the global primary energy consumption has been increasing substantially. And here you can see that predominantly this primary energy consumption has been dominated by coal, oil. These are all non renewables, right? And also, if you look into global country perspective, here we see that uh, global south countries, namely India, has been a predominant energy consumer. So the very possible solution would be then we need to reduce this primary energy consumption, right? But then scenario changes when we dig deep and see the per capita level consumption. Here we see that India is not among the topmost per capita consumer of energy, despite at a total level, India does contribute to a significant amount, and that means that whenever we want to tackle the demand side of energy transition, for India at least, we also need to make sure, and this is applicable to other countries in global south, that we take into account the well-being as well. So for that, what we are going to do now is basically share with you our next studies, next scenario study, where we will show you how in India we can achieve high well-being with a low energy demand. So for that, before we start the formal data sharing with you, I would like to request two housekeeping rules, namely, first is online participants. If you would like to ask question, please ask it via chat box. That would be a great help. And people here who have joined us in the room, please raise your hand so that we can ask this question. So after each of the presentation, we will have a quick round of questions, but not for long, around 5 minutes time. So quick clarification question, and if you have a broader question, or rather a very good question which would require further discussion, we will take this out into our Q&A session, which we have a dedicated time slot to. So with this, now I would like to go ahead with our next presentation. And for that, I would like to share again. Sorry, it's just a bit of technical glitch going on here. And I just need to share. Okay, hope you can see my screen. You do? Okay. So first is, what is the research objective we have? Or rather, I should directly go to the research question, as we have started a bit late I'm just skipping the objective part, but to briefly mention, our key objective for this research exercise was to evaluate how the existing model within EDIT community explore future energy demand in the global south countries. And second is also to assess the scenario result to understand the future residential energy demand reduction potential while maintaining decent living standard. Here, what is decent living standard? Decent living standard is basically the theoretical framework which measures well-being much precisely. Here, well-being does not only incorporate the subjective well-being, but it goes much beyond about objective well-being. And it's not only about meeting the basic human needs, but it goes much beyond that. And there are several studies and framework which are already existed related to DLS, which we are using to quantify the well-being associated with energy demand scenarios. And for that, we are trying to answer two precise research questions. First is how much energy demand can be reduced in residential sector by 2050? And to what extent can well-being be achieved by using LED scenario? Now, why building? Because in global south as well as in global north, building plays a significant role, especially the residential building. And also to the fact that building is one key sector where consumers, people, human, they actually associate it with much directly, or they use this sector much at a broader scale. And hence, even in India, although it's a fourth highest energy consumer, but if we consider the indirect emission, we see building plays a significant role. And that is exactly why we have incorporated or doing the exercise for building sector. And also, another last point I would like to mention that within EDIT networks, we have very good sectoral as well as individual analysis to understand the future energy demand scenario and also going ahead. The screen is not visible anymore. Oh, okay. Suddenly. Okay, I guess now it's okay. So this result is derived from high efficiency billing model because when we talk about billing, what is really important to understand that how floor area would evolve. When we talk about future energy demand, what we need to understand that without understanding the future floor area, it would be immensely difficult to evaluate the future energy demand of residential building sector. And here from the modeling exercises, we have seen that in Indian context, the residential floor area is expected to increase substantially. And here, although the majority of the residential building stock would still be in the rural sector, but the urban sector growth of floor area will significantly higher. Another point I would like to mention here, although you don't see it in this PPT, but the floor area of slum is also expected to increase quite substantially, which has a direct impact on well-being. And this is something, a common trend we have seen in countries in sub-Saharan Africa as well as in other South Asian countries. And this is something we need to take into account while designing policies as well. Because if we only consider energy demand perspective, here slum probably would not contribute much in terms of energy demand. But if we consider well-being and DLS, this is exactly where we need to look into, along with the overall building sector. So again, just a key insight. Second is when we go further into our detailed discussion of modeling exercise, we saw that cooling demand is quite substantially increasing in India. But here, let me just remind you, this is just the reference scenario. That is, if we continue with the present efficiency rate and trends, then what will happen in the future? But even with that, we see a substantial difference between two of our very own models, namely Safari and Image. So this data is actually just to show you that how different models produce different range of data and to let you know that we do not consider this is necessarily a bad thing, but rather we look into the modeling scenarios and understand why they are providing us different data. For example, the two primary reasons we figured out in this difference data range are: first is difference in methodology, and second is difference data usage. And as a result of it, around the 65% data range we are getting from a simple modeling exercises. And that kind of gives us a bit more work. That is, we need to harmonize our model if we really want to do a modeling exercise, or rather, we want to create a new scenario. Otherwise, we will keep on getting data ranges. But again, getting different data ranges or uncertainty ranges is not a bad thing, but rather it gives us a very precise what if insight. Now, I would like to pass the floor to my colleague and friend Alessio for talking about the further scenario analysis. And here I stop sharing my screen, or I can keep on sharing
Yes.
and you speak.
Can you hear me online? Yes.
Yes.
I'm going to present the work we did on scenario assessment for India, for the residential sector. And our motivation here is, as already Suran introduced, the need to jointly assess the access to decent living standards, which are key component, like for key requirements, material requirements for supporting well-being, and energy efficiency improvement strategies to simultaneously achieve climate targets and sustainable development goals in the global south. So we have here a set of 5 models, and this is a model intercomparison study that were able to assess this set of scenario to achieve high well-being with low energy demand, what we call high with low. Here you can see the models. So we have 3 global models as well as 2 national models for India, with also different approaches. And we tried here really to analyze the same set of scenarios with this model to get insight from the different perspective the models can provide. This is our scenario setup for this project. So we worked along 2 main axes, namely energy demand reduction and climate change mitigation. As you can see, we start from a reference scenario, which assumes the continuation of current trends and policies. And then in the energy efficiency scenario, we implement low energy technologies that can drastically reduce energy demand for buildings. And these include both improvements on the efficiency of the building shells, the building fabric of buildings, such as insulation, as well as improvements in the energy efficiency of heating, cooling systems, and switches to electrification and better efficiency of appliances. The other axis regards the improvements in access to decent living standards. And here we assume the achievement of decent living standards by 2050. Finally, we combine these 2 dimensions together in the high with low scenario, and we run scenarios until 2050 from the different models, focusing on 4 key dimensions of the residential sector, namely space heating, cooling, cooking, and appliances. Here are some of our key results from this study, and we are showing here the level of access to decent living standards. This is measured in terms of share of population, and we compare also results for different dimensions in 2020 with 2040 in the reference and decent living scenarios. The bars represent the average from the models, and then the error bars the range across different models. As you can see, despite our efforts in alignment model, there are still ranges that are produced, and this is actually also a part of the interest in this work, as we can also understand how these ranges look like, and also what are the differences that different approaches, different models, implementations can provide. So, however, all the models agree on the fact that even if we have an improvement in access to decent living standards already in the reference scenario, there is still a significant gap in many of the dimensions we included, and this can be filled only if we provide additional access to the services and components which define the decent living standards. We also investigated the dimensions of heterogeneities that characterize the different levels of access, and we found significant differences between rural and urban locations and settlements, but also between different household types and income level. And this highlighted also the fact that the gap is very different when we think about these different dimensions specifically, as you can see here in the case of air conditioning. And what is important here to say that the rural sector seems to be, to have much larger gaps, and also the low-income segments, they have much higher gaps in access that need to be filled in order to provide decent living standards. Another dimensions which is critical is also the geographical dimensions, and here in the case of clean cooking results, we can see that the differences are not only in rural and urban, but also across different states in India. And also in this case, while urban seems to be on the right trajectories to close the gap by 2040, there will still be significant gaps in some states in rural in the reference scenario. So how do we fill this gap? We basically need to provide improved services and access to decent living, and this requires additional energy. So you can see here the four key dimensions and uses that we have considered. So on the top row, cooling and appliances, and here the lines represent the averages from different models, and these shaded areas, they represent the ranges that we got. So what is interesting is that it's very evident that cooling is going to become the end use with the highest energy demand associated by 2050, and this is evident already in the reference scenario, and it's basically driven by increase in affluence and growth in floor space that Suran has been showing before. But if we want to provide everybody with access to thermal comfort and cooling, this energy demand will be much higher, because in the reference scenario still there is a big gap in access to cooling devices. How can we reduce this energy? So we can reduce this energy demand by implementing demand-side strategies, and you can see the effect of this demand-side strategy in the high with low case in the yellow dashed line, which is still slightly higher than the reference case, but much lower than the case where energy efficiency improvements were not implemented. Similar in the case of appliances and also heating and cooking. Here, the key is basically switching away from non-clean fuels. And even though this is the trend right in the current scenario, we need to go beyond and provide everybody with access to clean cooking fuels. This is the same set of results shown in a different way. So this is basically the change in 2040 for different scenarios compared to the reference. And it's basically also highlighting the fact that we have an increase in energy demand due to the provision of decent living, but by applying energy efficiency strategies, we can reduce significantly this increase in energy demand and even go lower than the reference scenario. There is a large range in some cases that is highlighted by the models, but in most cases there is also a consistent and robust trend for the different models. So the last slide I'm going to show, in the interest of time, we need to be quick. So this is the CO2 emission projections. In this case, it's just from the image model. So Vasilis later is going to introduce, also present these results more in depth. But again, here I'm showing the direct and indirect emissions for the residential sector. So this includes also the electricity, which, as you can see from the right chart, is still constitutes the higher share in terms of emissions. And we are showing here basically that there will be an increase in emissions already in the reference scenario, and even more if we need to provide decent living standards to everybody. But again, the demand side strategies can significantly contribute to reduce these emissions. Now we see there is still like a very large share of emissions in 2050, especially for electricity, and basically this means that our next step is to consider also the decarbonization scenario for the electricity supply side. Yeah, so to conclude, we have shown here a set of scenarios for the residential sector in India, and we have shown that demand will keep on on increasing, and we need to increase even more if we want to have everybody with access to the basic decent living standards which support well-being in different dimensions of the residential sector. Energy efficiency improvements can here play a big role in contributing to reduce the energy demand significantly and make it possible to achieve climate targets and also sustainable development goals. Finally, there is also a set of important co-benefits associated to demand-side solutions, which include also improved thermal comfort, health co-benefits, job creation, and reliance on proven technology. With this, I would like to acknowledge the great team that we had in this project, and also thank you for your attention, and happy to answer any clarification questions with Suran.
Thank you. Thank you so much, Alessio. So here now, just to respect the time, please feel free to ask your question through chat box, and we will take them all during our Q&A session. But since we are running a bit late due to technical glitches, I would like to move on to our next presentation. So may I kindly request Ashok Srinivasan from the Prayas Energy Group to basically present. And Ashok, you have already uploaded your slides, I guess.
Yeah, so while Sauran sets up the presentation, thanks for having us as part of this team and contributing to this. I think we're not, by Indian standards, we're not doing too badly. We're only 20 minutes behind time, so I think we'll make up. It's not too bad. I will also try and speed up, not spend too much time on my presentation. Should I just take the laptop in my hands to make it easier? Yeah. You can sit here. Yeah, so what I want to share very quickly with you is the results and some of the, more than the results, perhaps focus a little more on some of the insights that we have got from residential modeling that we have done using our model called PEER, which is one of the models that was considered in the presentation made by Alessio earlier. So this is something I don't want to spend much time on. This is just a little bit more about our models. I'm happy to share the details with you later, but just wanted to say that the bulk of what I'm presenting today is based on a recently released report or paper that we came out with called More with Less, which sounds very similar to High with Low. So because it's trying to explore the same question in terms of what we can do, how do we provide well-being without, or what will be the impacts of providing well-being under different kind of conditions. So I'll move on to how we have done the modeling a little bit, then talk a little bit about the results, and then focus on the insights that we have. So ours is at one level, I would say, simple accounting model. So we are just doing a bottom-up estimation of energy demand in the case of residential sector by considering, I would say, these four important parameters: the number of households that you have, the energy services that those households demand, and the penetration of different technologies that provide those household services, and specific energy consumption of each of those services together give you energy required for each of those services, which aggregate up to the total demand. And we have considered in the household context electricity and cooking fuels, various cooking fuels. The time period, we go up to 2041, financial year 2041, because roughly equivalent to Indian calendar year 2040. And we kind of, because we are also interested in looking at electricity a bit more deeply, we have kind of broken it down temporally further. A year has been broken down into 5 seasons, and each season is modeled by a typical day, which consists of 24 hours. So you get hourly electricity demand as part of this process. And we have also got state level disaggregation. Again, very quickly to tell you that we have modeled 5 different energy services: lighting, space cooling, refrigeration, cooking, and televisions. And for each of these, the point of the other columns is to say that we have not only considered one way of providing the service. So refrigeration is perhaps a good example to consider. We'll just look at that. So refrigeration can be provided by either direct cool refrigerators or frost-free refrigerators, and each of them can be of multiple star efficiency labels, as we know in India. So we have modeled them as 2, 3, and 4-star refrigerators for both of these. Similarly for some of the other appliances also. And obviously, these 5 energy services together do not make up the entire residential demand. So the rest of them is estimated more crudely by doing the bottom-up estimation for a reference year for which we have actual data, looking at the difference between them and using that to somehow estimate the demand that's going to arise out of other services, which we then project forward again using a set of assumptions. But the good news, at least we think it's good news, is that these services that we have modeled together account for more than 80% of the demand. So whatever errors in estimating the others will be within that 20% band. So, yeah, in terms of other little bit of description about how we set up the model, as I said, we've got broken up India into a bunch of states. So it's not strictly all the states. Some of the smaller states and geographies we have combined into larger regions. So effectively, we have 25 states, and each state is broken up into urban and rural areas. So effectively, we have 50 types of households in the country. India is represented by 50 types of households. And for each of these 50 types of households, we have estimated appliance penetrations for all of those technologies that we looked at on the previous slide by using what the latest data that we could find, which is NFHS5, which gives you for each of these things. And we have used per capita GSDP as a basis for projecting this forward in terms of how this is going to change in the future. Specific energy consumption, this is where I'll probably spend a little bit of time because we think that this is something that adds some value to the kind of modeling we have done. We have tried to estimate the efficiency of the stock of appliances that exists at any point of time through a fairly detailed exercise of trying to model the stock and flow of appliances. So we start off with the initial stock of appliances for which we assume a certain efficiency level. And then for the most energy consuming appliances are all covered by BE's mandated efficiency standard. So we kind of simulate BE's standard revision every 4 years, which is roughly what they do for most of the appliances over time. And using that, identify the efficiency of new appliances that are going to be bought. And then we retire older appliances, new appliances come in, based on which we calculate the weighted average efficiency of the stock at any particular point of time in a particular state, depending on its penetration of the appliances. And that's how we kind of arrive at the weighted average specific energy consumption of a particular appliance, which we use to compute the final energy demand. We've got kind of the same 4 scenarios that Alessio talked about in the previous slide. The names of the scenarios are slightly different in our case. So we have a reference scenario, a low energy demand scenario, which we call the desired efficiency trend scenario. And then we have a decent living standard scenario, which is a high consumption scenario where appliance penetrations go up. In the efficiency, low energy demand efficiencies are greater than the normal one. I'm not going into the details in the interest of time, but I'm happy to share all the details as required. And in the final one, of course, all these are combined together. So now let's look at what we get out of this. So in the process, essentially, what our model or our assumptions show us is that practically all households own fans. I mean, all households own fans, and almost all of them own TVs in urban and rural India in all our scenarios by 2041. Air conditioners, which is the appliance that all of us look to with great interest, currently or in FY24, it's about 9% in India, and across our scenarios, this goes up to anywhere from 50 to 60 odd percent. So there is a significant increase in penetration of air conditioners. There's a 12% CAGR if you want to look at the CAGR of penetration. And even rural India, by 2040, we see that in the high consumption case, almost half of rural India has ACs, and even in the reference case, more than a third of India has air conditioners. Refrigerators also similarly, you have fairly high penetration by 2040, more than 80%, about 80% of India has refrigerators in that scenario too. So basically, there's a reasonable increase in welfare in the country. But of course, as you might expect, there's significant variation across states. I'm sorry, the graphic may not be very clear, but essentially, obviously, as one would expect, penetrations of all appliances and modern cooking fuels increases over the time across all the states in both urban and rural areas. That's not surprising, but you do see huge disparities across states. So some states, as one might expect, Assam, Bihar, Jharkhand, West Bengal, etc., the increase in penetrations are not so high, and you don't see that much progress, while some other states such as Delhi, Haryana, Maharashtra, Punjab, Telangana, you do see significantly high penetration of appliances and many more, much greater use of these things. This is not a very interesting slide, just telling you a bunch of numbers that come out of our model runs and what kind of values we get. So essentially, residential electricity demand goes up from about 400 billion units, 375 to 473 in 24 across scenarios. all the way up to 572 to 878 BU in 2040. The Perhaps the only interesting thing here is really the first bullet point that, as we have tried to show in this graphic, the big part of the demand actually comes from these three appliances: fans, air conditioners, and refrigerators. So these three together account for more than 2/3 of the demand in every year, in every scenario. And I think it also works out the same way in most states. I have not shown the state-wise breakup here, but the same thing holds for states also. This is a little more interesting in the sense that it talks about the total energy demand, not only electricity demand. And as might be evident to some of us, cooking is really the energy service that dominates energy demand, particularly because currently a reasonable part of India is still using solid biomass as traditional fuels for cooking, which are highly inefficient. So if you look at the input energy content that's going in, that's very high. And because of the switch to modern cooking fuels, the total residential energy demand ironically decreases over time, even though there's much greater access and use of modern appliances, which is a good thing. And that is also evident in the second chart, where the blue that you see here is actually the biomass in the energy mix, the different energy carriers. So biomass, electricity, and a bunch of other things, LPG and so on. You can see that the biomass is falling rapidly, but electricity is increasing significantly, and LPG is also growing somewhat. So this is a good sign, but it's also interesting that the total energy required is actually falling over this time because of these gains. Now, for some of the interesting findings that we have, I'll just close with these 3 or 4 slides that I have. The first thing is, I think this goes back to some of the discussions we were having in the morning, and where Ritu said that one projecting based on history is actually very, very risky. This comes out very starkly here. So what we see is that in 2024, if I normalize these 4 values, the number of households with air conditioners, households with refrigerators, total electricity demand, and per household electricity demand, I normalize all of them to 100 in 2024. This is how they change by 2041. You see that the air conditioner owning households increase by 7.4x and refrigerator owning households increase by 2.3x. But the total increase in demand and per capita, per household increase in demand is much, much lower, which we thought is very interesting. And therefore, future estimations based purely on past trends is highly risky, and we need to be careful about it. And this is going back very similar to what Alessio talked about the high with low scenario. Essentially, what this is showing is a difference. How do I do that? Now?
Yes.
Thank you. Yeah. So the way we have tried to depict that is that in the high with low scenario, or the high consumption desired efficiency scenario that we have in 2040, compared to the reference scenario, you have about 60 odd million extra air conditioners in India, 60 million extra air conditioners, and you have about 25 to 30 extra fans in India, and about 20 odd million extra refrigerators in India. But in spite of this, the total electricity demand is actually lower by about 15 or 20 terawatt hours, which we thought was an interesting finding, and kind of backs up the kind of claims that Alessio was talking about in his presentation about high with low, where you can provide better quality of life without necessarily increasing in demand. So compared to reference, this is actually lower. So that's and of course this requires an effective energy efficiency regime which can implement these things. So that's the finding. Yeah, the last 2 slides I think I have. This is very quickly because we also do hourly modeling of residential electricity. Essentially, the finding is that the electricity's demand for residential services is going to get much peakier than what we have today, which has implications for network planning, demand side management strategies, how do you do power procurement to meet peak demand, and so on. This is a little bit about equity across states. This is perhaps not the best visual depiction of it, but what we have tried to do is, this is basically the reference scenario in 2024 and 2041. This is the high with low scenario in 2024 and 2041, with these where the bars again are errors and the ranges and so on. And what you can see is that in some sense the disparities between the 2 scenarios shows that The high with low scenario actually has lower disparity also. So the equity in some senses improved in the high with low scenario, in addition to the other benefits that we talked about earlier, which is not something we frankly expected, but there's an interesting finding that we get after looking at this. The last slide that I have is essentially saying that while there is great progress in the cooking energy side in the country, we still have about 27 million households, according to our model in FY41, that rely on solid fuels. And if one can call it a good news, the good news is that they're all concentrated in rural areas of 7 states. So one can have pretty targeted interventions to address the challenge by then. Thank you. And sorry if I took a little extra time.
Okay. Thank you. Thank you so much, Ashok. Now, may I request Kaveri from CSTEP to basically present insight from Safari modeling. Okay. Here is yours. Mm-hmm.
I uploaded 15 minutes back. It should be there.
And again, please ask your question in the chat box. We are taking count of each of your questions. These are really important for us, and we will discuss it very shortly in our Q&A session. Now, over to you, Kaveri.
Hello, everyone. So I'll be talking about decarbonizing India's residential building sector, insights and pathways that we found from our Safari model exercise. So this, I think, has been adequately covered by the previous speakers as to why building sector is an interesting sector in terms of emissions. So in addition to the direct and indirect emissions that Alessio was talking about, we also look at the embodied part of it, which comes from materials for construction, that is namely brick, cement, steel, and so on. And also the land use change emissions that can happen due to the type of urban planning that we adopt going forward, and the impact it has on the carbon sink availability, etc. So the research gaps that we aim to bridge with this buildings module of Safari is to see how we can include developmental goals, or in other words, decent living standards, as to what will be the material and energy needs to meet real housing shortage, the healthcare for all, education for all, these kind of infrastructural goals, as well as the very important thermal comfort goals on which we spent a lot of time in the morning session. So the analysis is not purely driven by GDP. There are these considerations that drive the model. In addition, we have also attempted to add some more nuances to space cooling demand estimation. We have looked at what would be the difference if we look at thermal comfort as a consequence of the building material and the envelope versus the appliance penetration based space cooling demand, and so on. The other interlinkages that we have, like I mentioned, is the impact of use of alternative construction materials on the industry as well as on the cooling demand, and the impact of compact versus sprawl on land use change. So to give a sense of the residential building sector's energy and emissions footprint, it constitutes about 25% of the energy demand, out of which 17% is what we call operational energy demand, which is basically cooking and appliances, and 8% embodied energy, which is the materials used for building new construction, and GHG emissions correspondingly is 28% and 11%. Now, that is why this is crucial for India's net zero target as well. And it presents a unique opportunity because, like in the morning, Satish had said, most of the building stock of 2050 is yet to be built. And this presents a unique opportunity for India to control energy and emissions from this sector. So a little bit about our model. We look at this interface between climate and developmental goals, and it's a system dynamic simulation model. It includes developmental goals, like I already mentioned, and it is a simulation platform in that it enables to create and analyze multitudes of scenarios to build strategies, and also to identify leverage points and trade-offs of the different policy choices made. This again is a brief on the model. We cover most of the economy-wide sectors, which is agriculture, transport, buildings, for industries, as well as natural systems like forest, land, water, and also resources like coal, gas, and other critical minerals we are integrating right now. And also, it gives the power sector based on the least power sector implications based on the least cost logic, and ultimately total emissions, and it's primarily driven by socioeconomic parameters and developmental goals. So the developmental goals I've repeated quite a number of times. So the drivers of growth are very much in line with sustainable developmental goals. So the housing goal, which is the most relevant goal here, is to bridge the real housing shortage, which is computed considering not only the aging of the current existing stock, but also degradation, congestion, and homelessness. And healthcare, which is looks at the improvement of infrastructure through adequate healthcare, which will result in three and a half beds per thousand, which is the World Health Organization norms, and educational infrastructure that is commensurate to improved enrollment ratio in the future, clean cooking goals, and food for all, and so on. There are a bunch of goals that are directly in line with SDGs and impact the energy system. Now, the socioeconomic assumptions of the model that are relevant to this module is: one is population, which is taken from World Population Prospects, and urbanization rate is assumed to reach 53% by 2050 and 75% by 2100. And GDP growth rate assumptions are based on MOFCC guidelines, which go up to 2050, and beyond that, we have taken the SSB public database. I think I have already covered this. We have various types of levers that can be used, and this is the causal loop diagram for the interlinkages that I had mentioned with power sector, industry sector, transport, and land module. This is how the model mechanics is working. So to give you a sense of the bridging the real housing shortage thing, what we have done is we looked at the sanction rates. The sanction rates in the model are calibrated to the Pradhan Mantri Awas Yojana, which started in 2015, and the target year is 2022. And beyond that, we look at what will happen with business as usual sanction rates, and also to see what are the sanction rates required to bridge the housing gap by, say, 2030, as per the SDG requirement. And this happens in the exact same economic categories as the PMAY, which is urban, economically weaker section LIG groups and MIG HIG groups, and rural. And this informs our built up area, essentially. And this also informs the material demand that the new construction drives, and what is the material adequacy that is provided by the industry, and whether the industry needs to ramp up their production to meet the material demands, and so on. And like I had already mentioned, it also the various assumptions we put on the urban forms that will be emerging based on the urbanization rate will tell us what is the land footprint of urbanization going to be, which will have cascading impacts. In terms of appliances and cooking, we have the heterogeneities, urban and rural, and all the different types of cooking fuels we have considered, and it's a standard way of computing cooking energy for each fuel. And for for other appliances, we have relied heavily on the IIASA database, and also some NSSO rounds to get to the urban-rural segregation. And ultimately, we get to the energy consumption from the appliances based on these different databases. Now, the new and interesting part that we have built for the building sector is to look at thermal comfort based on building envelope characteristics. So in the morning, this conversation came up one or two times that we have a building code called the Eco Nivas Samhita, which is what we have used to get to this RETV based on the material that is used for construction. And bottom up, based on the material used for wall and roof, we come up with the cooling load based on latent heat load and sensible heat load. And this cooling electricity demand, then we contrasted with the standard econometrics based approach of looking at appliance penetration in different heterogeneity, based on the heterogeneity of the model. I'll get to the results from this part in a bit, but just to give a flavor for the scenarios that we built using Safari, we have made two different scenarios. One is A, which is a little more conservative, more efficient usages of the current fleet of things, and decarbonization B is a little more radical in that you have more alternative construction materials and like more blended cement and little more radical things, like no new coal will be planned after the current coal plants that are in the pipeline and so on. And the difference is in the A scenario, we find that we can achieve 12% reduction in energy demand compared to reference, which already reflects a lot of ongoing policies. This is on top of that 12% reduction is possible, and 16% reduction in emissions by 2070 is possible. And for the more radical scenario, you can go up to 41% reduction from the reference and 51% reduction in terms of emissions by 2070. Now, the cooling demand results that we found interesting was that the black line represents the appliance-based approach, and the red line represents the thermal comfort based on the building envelope approach. So, as a whole, the overall households, we see that there is a gap in the thermal comfort achieved until 2040 when this crossover happens, and we tend, like if we go by the standard econometrics method, we are over consuming from 2041 onwards. So this we then looked at the lower income households versus the middle and higher income houses. So we find that in the lower income households, this thermal comfort needs is not really met until 2050, whereas in the MIG HIG house, this meets a little before 2040. So the result we saw before was a combination of these two things happening. And yeah, that's about it from my side. And this is just a conclusion that it highlights the need for cross-sectoral collaboration between sectors to achieve net zero emissions more effectively. And we have to also think about policy instruments that will drive the market towards these alternative developmental pathways and materials and so on. And cooling demand definitely has emerged even in our study as an important driver that will reduce operational emissions, that can potentially reduce emissions. And we also need to think more about building codes and what with the lens of thermal comfort for all as a developmental goal, rather than just push it based on, at least in the modeling frameworks, to just to push it based on appliance penetration rate. Yeah, so that's it from my side. Thank you.
Thank you. Thank you so much, Kaveri. Okay, now after this very thoughtful data exercise from Safari, may I kindly request Dr. Aman Malik to basically share his insight on overall Indian energy market. Energy as a sector. Right. Please. The floor is yours.
Yeah, thank you everyone, and good afternoon from my side as well. So my name is Aman Malik. I'm at the Council on Energy, Environment and Water, and today I'm going to present some preliminary work. So just to get a flavor, so this wouldn't be in depth on the multiple scenarios on how India can reach net zero. So its work is led by Pallavi Das, who couldn't be here with us today. So, but this is a joint effort which is being led by her. So, I mean, the context is, of course, that the target that the government has set up for us is very clear, which is 2070 net zero. But of course, how we need to get there um, is open for kind of discussion. And this is where you have scenario analysis from integrated assessment models, which can actually help. So we had a diverse set of scenarios that we actually wanted to explore. And I will come up to what these actually scenarios entail in the slide later on. So I'll skip this for now. So the main modeling tool that we use for analysis is the integrated assessment model GCAM, but this has been modified for India-specific circumstances, and it's called GCAM India. For example, we have cross-subsidization. We even have we disaggregate the building side and the electricity and the transport side to a higher detail to capture the nuances of the Indian market. Then, of course, we have a detailed energy supply, energy demand side, and and the energy demand is mainly driven by the socioeconomic data. And then, of course, the model tries to have markets for each of these products, and it gives then an endogenous price from this. And apart from that, there's also demand for agriculture and land use products, and then you also have the climate system built into it, just like a regular integrated assessment model. So, as I said before, we wanted to capture a lot of different types of scenarios, and we kind of started from a very aerial perspective. So, in the sense, we started well. We have different macroeconomic paths, basically different GDP growth rates. Then we have sectoral interventions, for example, only in the transport sector, only in the buildings and the industry sector. Then there are also technological interventions, the structural reform, for example. We have pricing reform, make in India, where India has a much higher share of manufacturing in the country. And we have behavioral change in terms of the life approach announced by the Prime Minister earlier. So in total, we have, for each of these, we have a BAU and a net zero. In total, we have 28 scenarios that we are actually working with. So just slightly more detail about what is happening in the different scenarios. Well, for the different growth rate scenarios, it's mostly clear. When we take, for example, in the sectoral intervention for the transport sector, there's demand reduction, there's higher energy efficiency improvement, there's more public transport, and similar. And in the building sector, there is again a higher energy efficiency improvement. What you can also change in the model is the set temperature compared to the flow space, and so on and so forth. The technological interventions are pretty clear. The structural reforms, and this is, I think, important, where we are saying we are removing cross subsidy by 2050. In the Make in India, as I said, there's higher share of manufacturing in the GDP compared to the reference scenario. And the life kind of then takes all the sectoral interventions that happen independently in transport, building, industry, and puts them all together. So this is kind of the scenario set that we had. And of course, for all these scenario sets, uh, we assume that the population assumptions are the same. The GDP assumptions are, of course, changing. Um, and you can see the growth rate that we have, for example, from 2020 to 2050, the average growth rate in GDP that we're using is around 6%, which kind of plateaus and decreases then to around 3.3% um, in the future years. So what are the key results that we are seeing? And the first thing that we are seeing, of course, this is the BAU scenario. The lines represent the different scenarios, and what you see is that the life scenario represents the highest emission reduction. So this is 75 compared to 100%, which is in the BAU scenario. And of course, other scenarios which are either high growth, or where a lot of growth is happening in urban areas, or a lot of manufacturing is happening, they have much higher emissions. The second thing what you can also see is that that the future emissions for India will be lower than historic emissions under all scenarios. So the line just above 50, so India emitted from 1850 to 2019 around 53 gigatons of CO2. So if you look at the reference scenario again and add all these emissions from 2020 to 2070, they are lower than this line, which I haven't shown here, but you can imagine it. And of course, as I mentioned in the last slide, the Make in India and the high growth scenario have the higher emissions among all sectors, because there is more energy intensive growth kind of that is happening. Now, if we look at the carbon price, and again here I would take it slightly with a pinch of salt, in the sense that this is trying to get you just a flavor of what is happening. So here the carbon price trajectory here starts from 2040. So this is where we are assuming. So we assume for all the scenarios that the emissions peak in 2040 and then decrease to net zero in 2070. So all scenario except for the one with CCS, they have a similar carbon price in 2070. Except, of course, for the CCS one, where the availability of CCS means that the carbon price is actually then much lower. And in the initial year, the high growth and Make in India scenarios again have a higher carbon price. And this is again happening because of the high energy intensive growth rates, you need kind of a higher carbon price to decrease your emissions. Now coming to electricity generation, in the net zero scenario, you see that The electricity generation is, of course, also higher in the Make in India scenario because of much higher share of manufacturing. And in the live scenario, this is much lower, which kind of goes in direction what I already pointed out before. And this is now my last slide. So some key insights for the pricing reform scenario. What we see is that if you remove cross subsidy, then the grid cost actually becomes higher, and this leads to lower electricity consumption in the building sector, mainly in the residential sector, and this eventually leads to higher penetration of rooftop PV in building sector. So the model tries to already show this very kind of interesting question that we always have. Okay, what are the effects on penetration rate? What are the effect of emissions once you remove this cross subsidy that we see is kind of very special characteristic of the Indian electricity system? For the live scenario, which is kind of gaining more and more momentum, we also saw in the COP that kind of where the Prime Minister was highlighting how the COP, the live scenario, demand reduction scenario is important for kind of the whole world. We saw that it led to our overall reduction emissions because, of course, the various demand side measures that were in the scenario, and the carbon price even for such a scenario is actually lower in the near term. And that's actually the end of my presentation. Thank you very much.
Thank you so much, Aman. This is really, really insightful. And this is your coffee as well. Okay, thank you. And now we move on to our very last presentation of the day before we do our Q&A. That is, now we invite our very own Vasilis from the image team to share some knowledge about IAM modeling exercise and also looking Indian energy market from a global perspective. It's at the top. Okay, just give me a second. Over to you, Vasilis.
Thank you. So, hello everybody. Thank you for inviting me to talk here today. So I was asked to present something on Indian energy scenarios. So I'm going to present some results about energy demand and emissions according to the image model. So just a very quick introduction for those of you who aren't familiar with this model. It's an integrated assessment model developed by the Netherlands Environmental Assessment Agency. And basically its purpose is to model the interaction between the human system and the natural system, which the human system is made up of agriculture and land use on the one hand, and energy supply and demand on the other. You can see that in the red area. And then the natural system covers land cover, nutrient flow, atmosphere, and oceans. And that you can see in the green area. And basically the human system and the natural system, they interact through emissions, but through land cover and land use, but also through the flow of different nutrients. So ultimately, this model, its purpose is to be used for long-term global scenarios. So our time frame is at least 2050 going to 2100, and it's generally been used for global to assess global environmental issues in these large-scale assessments, such as the IPCC, the Global Environment Outlook, International Resource Panel, and so on and so forth. And it's basically used to explore possible futures across different narratives, and that's why our main methodology is scenario analysis, where we compare outcomes based on different narratives. Now, specifically for this presentation, I'm just going to focus on the energy supply and demand aspect. I'm not going to present other parts of the model or other results. So focusing onto the energy supply and demand, this is a schematic of our energy model. And basically, we cover everything all the way from the supply, from resource production, through primary energy supply, energy conversion, final demand, and then finally energy services. So all the way from mining the coal or drilling the oil or harvesting the solar power on a PV unit, all the way to the provision of a passenger kilometer, a freight kilometer, a meter cubed of residential building heated, and so on and so forth. And in there, we try to look at all of the relationships, and the provision of energy services links all the way back to resource production through prices. So as you use more energy, you deplete a certain energy source, its prices go up. This may affect the way you demand energy by making other energy carriers more competitive. Or if overall the provision of the energy service becomes very expensive, there is a price response to that. You may simply demand less of it. So this is an overview schematic of our energy model. The scenarios we run, this is basically a different way of showing the table, the schematic that Alessio showed before, but I'm going to be presenting results for a number of baselines. So we have a default baseline, which fundamentally is based on an SSP2, together with current implemented policies. And then there's two variations on that. The tech, where we also have measures to increase energy efficiency. So this may be technology improvement, or specifically in the building section, also insulation is accounted for here. And then we have the DLS scenario, which is where we have measures to achieve decent living conditions. And then underneath, there's a bunch of variations on the baselines, basically mitigation scenarios where we meet a 1.5 degree target. And for those of you who are so inclined, that means a peak budget of 650 gigatons of CO2, end of century budget of 400. And we do this for all of the scenarios. And then there's one final one, the high with low. As Alessio said before, this is basically a combination of the tech and DLS together. So high access with low energy use. So moving into some of the results, here I'm showing the service demand for the transport sector. And what we see is each panel is, so first of all, we have the total passenger transport and then the components that make it up, aviation, railways, road. This is specifically for India. And I'm showing the default baseline and the decent living. And basically what we see is that applying the decent living just leads to a slight increase in passenger transport in the short term, which is reflected through road passenger transport. Basically for us, the threshold for decent living transport is 8,000 passenger kilometers per year. India is already in the baseline trajectory. It's approaching that. The decent living, there's just a sudden kink. But you see for the rest of the projection, they're actually identical because India in our projection would meet that anyway by mid-century. Then moving on to the residential sector, which is a little bit more interesting. Here we can see a number of access indicators: electricity access, clean cooking, fan, air conditioning, refrigeration, television. For the time being, I'm just showing the default scenario. The black lines are urban households. The green lines are rural households, and the different shades are income groups. So the deeper shade is richer households. So the first thing that we see is that urban households generally have higher access than the rural households. The black lines are higher than the green lines, and the richer households, as expected, they also have higher access. The deeper lines have more than the lower shaded lines. So we see that for the default scenario, while electricity access is met fairly early, fan access, television access, those are also pretty high. Clean cooking, air conditioning.
And we lost it at a crucial juncture. Now we are back.
Yes. So this is what we see for the default scenario. And now we can see also the decent living, where as prescribed by the scenario, access for all of these indicators increases rapidly. For clean cooking, we meet it by 2040. For appliances, by 2050. That's a constraint that we simply set. And yeah, we can see that electricity access and television access, those are actually already met in the default. They don't change between the two scenarios. But for the other indicators, we do here change. So what does this mean concerning energy demand? So here we can see first for the baselines, the energy demand of different sectors. So I've got commercial buildings, industry, residential buildings, and transport. And the different colors are different scenarios. So what we see, focusing first on the black lines, is that generally we expect in the default scenario the energy demand will increase across all sectors quite significantly. This is because of assumptions of increased economic growth. On the efficiency scenario, so that's the blue line, we see that generally the blue line is lower than the black line because of the technological efficiency, roughly somewhere between 10 to 20% reduction in energy demand compared to the default, depending on the sector. The decent living, this is where it starts getting more interesting. As expected, when we put decent living constraints, this does increase the energy demand. And that's particularly clear on the residential sector. So that's the third panel, where you do see this sudden upwards shot of residential energy use. This is to meet the decent living standards. There is also a little bit on the transport sector, a higher, an increase in the energy demand, but because transport, as shown earlier, already almost meets decent living in the baseline, it's only a little bit higher than the default scenario. And for commercial buildings and industry, the decent living scenario doesn't make that big of a difference. In this version of the model, we haven't put in feedbacks from increased requirement for air conditioning, increased requirements for cars, what this may mean for industry. In a version of the model that we're working on right now, we are hoping to capture those feedbacks. So you would see an increase in industrial energy demand, not captured in this version. So looking into the mitigation scenarios, so what we see is, first of all, is that generally, all of the scenarios on the mitigation side, they are lower than the baseline. This is because of price responses, because a mitigation scenario requires a carbon price, as was also shown in the previous scenario, and this ultimately does reduce your demand for certain energy services, especially the excessive demand beyond decent living. Then what we see is what we see here is the high with low scenario. So this gold-yellow scenario, this is the most interesting scenario because it does show the lowest energy demand, even though it does also meet decent living. So what we see with a high with low scenario is that you can meet these decent living constraints while even having a very low energy demand. And in fact, we see that the residential energy demand is roughly at the levels that it is today. While meeting decent living, increasing generally energy use services, it doesn't increase energy demand. And this is because of big improvements in efficiency, the phasing out of traditional biomass, which is extremely inefficient, as was mentioned before. So this is quite an important insight, I think. So moving into what does this mean concerning energy demand from energy carriers, I thought it would be interesting to talk about this at this point. This is for the entire Indian energy system. The final energy demand, secondary energy demand, the energy carriers across all of the different scenarios. And what you see in the default, you generally have a continued use of charcoal, an increase in liquids, an increase in natural gas, also an increase in electricity, but fossil fuels still make up at least 50%. Well, fossil fuel direct use, there's also a lot of fossil fuel use in electricity. Then moving into the 1.5 scenarios, we find that, first of all of the 1.5 scenarios decrease the overall energy demand, as was also shown in the previous slide. The default 1.5, that does have the highest energy demand amongst all the mitigation scenarios, with as expected, the efficiency scenario and the high with low having even lower demands. The decent living, funnily enough, even though you are meeting decent living constraints, it has a slightly lower energy demand than the default. And this is because of the phasing out of traditional biomass, which is really inefficient. So you clearly see that in the decent living, that traditional biomass, that green area in the top, is phased out by mid-century. So this leads to efficiency improvements, leading to a lower overall energy demand. So I think this is the final result I'm going to show. I just thought I'd show, okay, what about emissions? So here we see on the top row for India, the emissions from energy demand and energy supply for all the scenarios, and the bottom row, just as a comparison, what we see on a global level. So default scenario, India and world, we generally see an increase in emissions. That's not that surprising. Default scenario, default 1.5, we do see a rapid decline in the emissions, both of India and the world. This is to be in line with the carbon budgets that we assigned to meet the Paris targets. What we see is that the net zero year for the world, this is a global optimized results. So what we see for the world, net zero is met around 2050, net zero for the energy system. While for India, that comes much later. It's towards the end of the century because there are continued emissions from energy demand. There are negative emissions from energy supply, both in India and the world. This is basically bioenergy with carbon capture and storage. And then when we start moving into the efficiency, decent living, and high with low scenarios, what we see is that the net zero year for India is pushed forward between 2060 and 2070. So it does make quite a big difference. The net zero year is pushed by 20 years or so, depending on the scenario. With the high with low generally showing the net zero year being around 2075. I did have some more results. So kind of looking into these emissions in a little bit more detail so that we can understand what's going on. Here we see the energy system emissions in a baseline and a mitigation scenario, and I'll just walk you through the results. So in the mitigation scenario, as expected, energy system emissions decreased quite a lot, reaching net zero by the end of the century, as was shown before. In the decent living scenario, what we see is that generally the energy system emissions do increase by about 5 to 10%, which isn't that much given, and obviously the net zero year also shifts by only a couple of years. So what we see is that decent living doesn't make the climate goals completely out of reach. It's only a couple of years that, it's only 5 to 10% that emissions are increased while providing a lot of important development needs. So decent living isn't completely in contrast with climate goals. The efficiency scenario, this as expected reduces the emissions a lot, both in the baseline and the mitigation. And as was explained before, the net zero year is pushed 30 years earlier. And then finally, the most interesting scenario, the high with low, you meet decent living conditions in the residential sector and in the transport sector. And you also meet the net zero year earlier on than your default scenario. So this ultimately means that the meeting climate goals is going to be cheaper than in our default scenario. That's another way of seeing this graph here, meeting a 1.5 target at a reduced cost, not taking into account what costs may come with achieving this high level of efficiency, but from the broader energy system, it's at a way reduced cost. But the reason we see this rapid decline isn't because of the transport sector, isn't because of energy demand, it's because of energy supply, it's because of power system decarbonization. That is really the secret here, especially the negative aspect. It's bioenergy with carbon capture and storage. So in conclusion, energy demand is projected to increase a lot. It's primarily driven by cooling and appliances in the residential sector, but also in the transport sector a lot by further access to passenger kilometers and freight kilometers. Basically in all sectors, we're expected to see an increase. Meeting decent living standards pushes up energy use and emissions, particularly in the residential buildings, less in transport, and it may delay the achievement of climate goals, but it isn't critical. It doesn't make them impossible. Efficiency improvements above baseline and increased electrification reduces this effect, leading to a meeting of climate goals even below the default setting, and it can contribute to other co-benefits, be it air pollution reduction, the increase of so-called prosumers. So this leads to broader knock-on effects concerning affordability in households, ability to earn income, and things like that. But the secret is to achieve the 1.5 degree scenario as well as decent living. Electrification of energy services is important. So access to electricity, but also access to a reliable electricity at a high enough bandwidth in order to make sure the households can meet their required energy services. So there's also an increase in electricity supply and making sure that this electricity supply is decarbonized. So in the projections, electricity demand and the supply is projected to increase rapidly. Making sure that that increases rapidly while also decarbonizing, that's the real challenge here. And that's all I had to say right now. Thank you very much.
Okay, thank you so much, Vasilis. This is really, really insightful. And now it has opened up, I guess, a lot of our queries and questions about the true potential of demand side measures, and especially in case of global south countries. And clearly from our modeling exercises, it seems that it is indeed possible to apply demand side measures, and because not only we can, but also it would substantially benefit both globally as well as people in global south. I now like to open the floor and give the floor to the audience, both present in the room as well as joined us through online. But first priority is online, and may I kindly now request my colleague Alessio to read out some question because I haven't been able to follow the chat box. So
Yeah.
over to you, Alessio.
Thank you very much, Suran. So we had already a lot of questions and a lot of activity going on in the chat, which is great. So some of the questions were already answered, for instance, about the presentation that you, Suran, and I did. So about basically the importance of electrification and how we consider that in our scenarios, as well as other fuels and phase out of fossil fuels and traditional biomass. There were then some questions on specific models, and maybe here we can quickly go through them. So there are some questions for the image presentation, then some for the Safari. So question for Vasilis here. What do we mean by DLS for transport in terms of the narrative actual mechanism? That is, given how transport is a derived demand and the economy would only grow in size, how should capping at 8K ppm per capita can be interpreted?
Okay, so I can be heard if I talk from here, right?
I guess so.
Okay. So first of all, it's not capped at 8. It's that's the floor. We force that, and then it could increase. How transport is derived demand and economy would only grow in size. I mean, yeah, we consider the economy to continue growing. We just make sure that the 8 passenger kilometers is it's a floor. It's not a cap. So we force that demand which isn't met in the default scenario, and then it can increase further. I hope that answers the question.
Yeah, please reply on the chat if this is not the case. Hopefully, yes. Then there is also a question for the Safari team, so for Kaveri. One step shown in the Safari model is an existing new stock of housing requirement, which is, if I understand correctly, estimated by the housing shortage based on the population growth projections. I think this step is extremely important for modeling demand, making the representation of end-use service demand possible. And then a follow-up question, will you also agree that real estate policy can also be a fiscal tool, selling land and levying on property taxes? How luckily can we trust a future scenario where housing supply will really match housing requirements?
No, for sure. I agree that it can be a fiscal tool, but unfortunately we are unable to represent it in our modeling framework. Given that we do have history of policies like the PM Awas Yojana, which is Housing for All scheme in India, it can be a policy-driven scenario as well, I guess. But I don't know for how much time into the future we can rely on such a thing and not go on towards fiscal tools. We don't have that in the model. It's a short answer, but we should in some way for the future.
Great. Just one last note. So we recently published a review paper with many of the colleagues that participated today in the workshop, and it's about reviewing the building sector modeling and identifying the key gaps and opportunities for improving the representation of the building sector, and especially also the different policy strategies that we have available here. So I posted the link in the chat, and hope this can be also an interesting reading for further deepening this topic of building sector energy demand modeling. Over to you, Suran.
Okay, so do we have then all the questions answered?
I'm also answering in the chat some questions.
Yeah.
Okay, but it would be good now to bring this up. So
Yehoon asked about how come in the mitigation DLS demand for the residential sector is lower than the default, even though efficiency measures are taken into account. And this is because of the substitution of traditional biomass. So the DLS scenario moves to cleaner cooking and heating fuels very rapidly, which are way more efficient, and that leads to the lower overall energy demand.
Yeah, and I just have a follow-up question. So you basically are forcing biomass out of the system?
Yeah, we basically say it's not allowed anymore.
Okay.
Yeah.
Okay.
And it's a consistent finding among all the models. This
Right.
energy demand.
That it's reducing, right?
Reducing.
Yeah.
I mean, but that is a good follow-up question because, yeah, we're not looking into what policy would achieve this, what is the policy cost. We're just literally turning off in the model the availability of the fuel. It's as simple as that.
But at least in the case of fear,
Yeah.
it's also based on the recent changes that have happened post Ujjwala, which has actually accelerated the shift away from solid fuels to modern fuels, even in terms of uptake. Of course, it is the ownership of LPG, access to LPG connections is almost 100% now, but usage is still much lower. But the trend is that even that is increasing, and that's what we've projected forward. So in that sense, it is kind of, it's not, I would say it's not artificially forced, it's kind of extrapolating the recent trend over the last 4 or 5 years.
But then in the model, you still force it, right? So you'd say, well, in this year it cannot be more than this, or you say in 2050 it has to be zero.
No. So we don't have any normative targets.
Okay.
So we just extrapolate recent trends and take it forward. And that's why we don't reach 100% even by 2040. In 7 states, we find that it's 90-odd%.
And in the model, is there fuel stacking allowed?
No, we haven't modeled it. The modeling platform we use has the capability to do it, but we haven't done it yet. There's just no data available for it. We have to just hook up the data. So
I hope you could follow the in-room discussion. I hope it is audible clearly, right? Okay, excellent. Because there are some very good questions around, and I should also mention that in the audience we have Dr. Ritu Mathur, who works with Niti Aayog, and Dr. Prabal Ghosh, who works with IID. Both are very renowned think tanks, as well as policy researcher group who directly works with Government of India. And I also would like to encourage the online participants to, if you have any particular policy related question or modeling related question which you would directly like to ask the policymakers or experts like them, feel free to do so, because it is also a rare opportunity. It's great that they have taken their time out to stay for us this long, because we had a very long workshop, closed group workshop in the morning, and then in the afternoon we are having this hybrid session. So please do not lose your chance as well. And I have a bit of bigger question, and Alessio, please keep on looking if we
There's
get
another question on image,
Okay.
but maybe we can just
no, go ahead
do
with
in
the
chat.
image, and then
we can do in the chat.
Yeah, I'm responding already in the chat.
okay, but it's great that if we can bring all the questions here, so we have a good session. Yeah.
Okay, so yeah, Mohammed is asking how image is categorized. Is it optimization, simulation, or if it has other elements? So the energy part of the image model, so the results that I presented, that's a recursive dynamic simulation model. So it definitely does not optimize to anything. It's not an equilibrium model. It's a simulation model. Other parts of the image framework have different philosophies. So for instance, agricultural trade, that's much more on a computational general equilibrium aspect. But the energy aspect, a recursive dynamic simulation.
Excellent. Yes, Dr. Malik.
I have a question. I mean, there was some similarities if you look at the work, for example, you did, and some of the scenarios are presented in which we assume certain energy efficiency improvements, which happen, let's say, in the building sector. And I mean, in the model, we just say, well, it changes from this to this percent, which perhaps without explicitly saying how it happens, right? I presume. So I'm actually interested in exactly these numbers, because this is kind of gets into the core of modeling and the way models think of how much energy efficiency improvement we can think. So as a modeler who was modeling these energy efficiency improvements, what was your approach to this?
That's
take
please.
this one? Yeah, thank you very much. This is a very good point, and I think more generally this question is about also exogenous, so external basically inputs and assumptions to the model versus endogenous representation of specific dynamic within the model. So I think this is a very relevant question. Often we still rely, I think, on these exogenous projections and assumptions, which I think is good for answering question of this what if type. So what if we implement energy efficiency improvement to this extent? What is the effect on the energy demand? I think there is also research directions in trying to better endogenize, so to better basically describe specific dynamics and phenomena, and also better represent the decision of households in some cases. So this is done, for instance, by using discrete choice models, or in some cases, we also had a chance, for instance, to experiment by coupling, soft coupling an agent-based model with basically our simulation model for the building sector. And I think this coupling exercise, while they're challenging because of the different nature of models, can help in basically having different insights, more on the infrastructural side or energy system side on one end, and on the impact of different behaviors and maybe lifestyle changes on the other. So I think it's we should probably also foster this discussion and try to understand what are the assumptions from different models, how do they compare with the results of the the models which represent this dynamic endogenously, and this will probably be a very good learning exercise for all of us.
Yeah, that's a very good point. But before I respond, I see Ashok has raised his hand. No, please go ahead, and I can do.
Yeah, I just wanted to share how we're doing it in here, because that's one thing that we took a little bit of effort in trying to do. So there we have actually tried to, as far as possible, simulate what B is actually doing. We actually follow this B, as you probably know, there are these whole bunch of appliances for which B as mandatory efficiency standards, which means by law you can't have appliances in the market that don't meet those standards. And they've modeled those various star levels separately in our model. And we assume that the BE efficiency standards are revised at the frequency at which they have normally been happening. And even the way they are revised is basically what they do is they just ratchet it up one level. So what was 5-star last time becomes 4-star now, and so on. And a new 5-star comes in. We have replicated exactly that process. Every 4 years, the new stock, that new appliances that get bought after the revision of the standard adhere to the new standard. Until then, the appliances are basically they adhere to the.
Ashok, could you please speak up? Online
sorry.
cannot hear you very well.
Yeah, so what I was saying was that we have tried to simulate what actually happens in India in the form of how the regulator of efficiency standards in India actually implements efficiency standards for appliances, and incorporated that into the stock flow model of appliances that we have. So the flow of appliances, the efficiency of the appliance flow is determined by the efficiency standard as imposed by the BE. And over time, and of course, so the historical things that exist at the start of the model period, we assume a legacy efficiency of the stock, and we keep calculating the weighted average efficiency over the years. And that's how we compute the efficiency, and that is how we see the efficiency improvements happening in our model.
Here, I mean, just to reflect on this, and then Benny asked a really amazing question, which I want to discuss here as well. But just a quick reflection on your question, Aman. I mean, I'm not going to add on how we deal it with our model, because we do it in different ways, and there are 1,000 other ways in 1,000 other different models. But what I would really like to mention here, that when we are developing scenarios, modeling scenarios, as a modeler, we need to be mindful of what are the objective of the scenarios. Why I'm saying this, because for example, in case of both demand and supply, what we look like to somehow see what are the highest potential, right, for decarbonization or for reducing demand. If that is the question, in some cases we need to be innovative as well. And let me give you one quick example from high efficiency building model here, which is our model together with Central European University, Diana Urgevursat, that what we tried to look into that initially back in 2012, where we are building this model, we understood and we assumed that, in South Asian region and this global South countries, passive houses type construction can never be built, right? And our assumption related those data on energy intensity are accordingly assumed. But then starting from 2018, we were kind of amazed, like a country like in China, they have a significant amount of passive house building stock, which were beyond our imagination of modeling assumption. So in some cases, as a modeler also, we need to be innovative while we design our scenarios, because sometimes when we probably take too conservative approach, and this is a criticism for me myself as well, I would say. But in reality, sometimes the technological innovation, as well as a personal scale, as a lifestyle innovation, goes much beyond than the reality. So this is something we probably need to consider. That's number one. Number two, I think it is really, really important for countries like India that we do consider the economic drivers. And it's not about only behavioral changes, but also economic drivers in terms of price sensitivity, because Indian market by nature is price sensitive. And this is very evident through the appliance market, especially the five-star appliances cost much more. And hence, in more of the cases like residential cooling, we see that dominated by two-star energy efficiency appliances. So this is something we also need to consider in our scenarios. So just these are the two key points I would like to mention. But also now I would like to really take Benny's point and then come to Dr. Ghosh and Dr. Mathu about this. So Benny asked the question that what policy questions do you think energy demand model should answer to an Indian context? And also, what do policymakers find important, like taking into account that this model can tackle well-being development and energy system pressure together? So, Dr. Mathu, can we go with you first?
Yeah, so I think one of the things which was mentioned in the morning as well. I think as we are looking at India's development, the issue about empowering households and the economy uh, in economic terms is definitely a question from the policy side. So which also brings the livelihood aspects and the make in India aspects, etc., come into the structure of well-being or development. So from that perspective, the prime question that becomes meaningful in this context is how much is that level of demand? We are doing a lot on the supply side. We keep on saying ABC are the technologies on the supply side which can meet and be the solutions. But on the demand side, it is much less explored, much less examined. So I think having a better judgment of what the demands could be under different ways of looking at the aspiration levels and levels of well-being is definitely something which is of immense use. The second aspect is also about the when. So what do you do in the short term vis-a-vis what do you do in the long term? Whether you do a set of packages of complementary policies or you do one policy at a time? And what would be the implication of doing incremental things in a staggered manner vis-a-vis a package of policies? Uh, these are questions which are less explored and which could be very important from the policy domain.
Excellent. Thank you. Thank you, Dr. Mathu. Dr. Ghosh.
So, I'll,
We need to speak up a bit.
yeah, so can you hear me?
Do you hear well? Okay, yes.
Yeah, so I would, make my point. I have some points to make on the earlier presentation,
Sure.
but I'll make it through answering these questions. One, when we, address Indian policymakers, first thing is important is that we need to, replicate the reality, the Indian reality, the baseline, So if the policymaker sees that certain basic things or how they visualize the situation here is not reflected in the scenario, they are likely to warm up to the policy suggestions. So that is first thing. Second thing is that you need to understand what are the options available to the policymakers. So we can give a very good academic scenario which makes a lot of sense and a lot of nuance, but the policymaker will not know what to do with that. So we need to package it along with levers that are there with the policymakers. We have to understand and understand the levers that are there. So whenever we come out with modeling results, when we present it to the policymaker, Yeah. So two things. One is that in a developed country and in a developing country context, there's two basic difference. One, in the developed country, the per capita income level is very high, so the purchasing power is very high, and which is low in a developing country. And the population density, say in Europe or America, which is in a developing country like India, subcontinent, very different. It's a very densely populated region. So what are the implications of the two? First thing is that since the purchasing power is low, so to expect that you can have this decent living standards be reached immediately, because you're showing that there's initial immediate rise and then there's a convergence. This is an unrealistic situation, so it is not possible that in the next 1 or 2, 3 years, government of India can force this decent living standard scenario. So the more realistic thing would be to set a target, say 2030 or 2050, the decent living standard should be reached compared to whatever it is there today. The two advantages that by 2030, 2040, the per capita income will be good enough that people can adopt the decent living standard by themselves or with some government support. So that's a more realistic scenario, doable scenario for the policymaker, right? So if you talk of this minimum transport requirement or the minimum flow requirement or say the minimum appliance use, so these all is more relevant in say something like 2050 or 2030 kind of a thing. So that is the per capita income kind of a thing. The second is the population density. So what happens is that so when you talk that we require so much minimum flow size, if you look at the Indian cities, they're so densely populated. It's unlikely that you can have houses that are very, very spacious. There's, prices are going through the roof. Other thing is that it is more likely a scenario would be that instead of this Delhi expanding, or the Bombay expanding, or this Chennai expanding, or Bangalore expanding, more cities coming up, the two-tier cities coming up. So the jobs shifting there, people shifting there. So then it is not likely that they are going to have minimum higher level of transport requirement, because see when we talk of efficiency in the urban design kind of a thing, we say that we develop cities in such a way that your transport requirement is very less, and yet you are able to meet all your demand requirements. So therefore, then I think philosophically, one doesn't require that much high amount of transport requirements. So, 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 it may be right in a European or American context, but may not be right in this subcontinent context, because the space land is very of high value and less availability for residential purposes. So that those are the two aspects I would say that you can think. One is if you just change the scenario, instead of immediately reach it at 2030 or 2040 or 2050. See in the reference scenario when we are reaching that decent level, then maybe by normal situation that is more doable. If we are not reaching by 2030, 2040, so what can be done? And then the low carbon thing, like efficiency kind of a thing. So that's it. And one question I had regarding Prayas' scenario is that your scenario showed that the decent living scenario and energy efficiency actually brings down the, it's a much better combination. So is there a rebound effect in the model? Why that thing happens?
No, I mean, we have not explicitly modeled rebound, but essentially what it's in that sense, straightforward set of assumptions that we made. That in the decent living, essentially what happens is that people are both owning and using appliances more. The reasons for that could be either greater affordability or due to rebound or whatever the reasons may be. But essentially, you're owning and consuming more appliances, but at the same time, the efficiency of those appliances is lower. And essentially, the efficiency improvements override the increased ownership and use of appliances. That's basically what we do.
And
We of course have those two scenarios separately also. If you only increase consumption, obviously demand goes up. If you only improve efficiency without increasing consumption, demand goes down significantly.
But if your appliance ownership goes up, which is say costlier appliances, so that can always affect your household saving and then.
Yeah, so that's we don't have those feedbacks built in.
Huh.
So this is assuming that due to whatever external factors, people are able to afford and use it.
Because I expect efficiency to bring gains. So when you have efficiency, you are saving money, so you're likely to increase your expenditure. So there's a gain there. So I was just thinking whether that gain outweighs.
No, that feedback loop is not there.
Okay, but still we have.
Yes, Dr. Mathur.
Just to sort of take an anecdotal point from what was mentioned and raise the question on transport. So on transport, we saw a very small blip in terms of the additional requirement because of well-being. But one was again wondering because of the kind of situation that you are likely to have in a developing country context. If you're looking at more mobility or more public transport, etc., being provided, is that simply well-being? Is that the definition? Or, for example, today, if I look at a bus, maybe a seating capacity is 40, but actually 100 people are traveling in the bus. So, with some standing, some on the roof. So that's not to me well-being. It would also translate to maybe 2 such buses to be able to give people well-being. Does that sort of get factored in terms of when you're looking at the shifts of comfort as well coming in? That's one question, and the other question was related to the peer model and the other household models. There was convergence in terms of a reduction happening overall, but does the reduction in residential in all cases also override the reduction, I mean, the reduction in residential override all other sectors as a whole?
Well, we are in the process of modeling the other sector,
Okay.
so we'll tell you when that's done.
Okay.
But it's highly unlikely.
Yeah.
It's highly unlikely.
The reduction in because of the efficiency improvements.
Yes, because in your scenario, it did override all the other sectors as well.
The thing is, in our scenario, we have efficiency improvements across all scenarios.
Yeah.
So the other scenarios that across all sectors, sorry. So the other sectors did also reduce their energy demands. I think industry and transport tend to be larger than the residential sector. So efficiency improvements just in the residential sector doesn't drastically change the picture.
Okay, that's really, really great points. And just a quick reflection on Dr. Mathur's question and also a quick reflection on Dr. Praval's reflection. First is Dr. Mathur's about comfort, like how do we define comfort and well-being, whether it gets factored in. To some extent it does, and to some extent it doesn't. So sorry for this vague answer, but that is what it is. Although I personally do not model transport directly, I do model well-being and health-related impact due to active transportation, but that is different. But what you are asking question is about the quality of well-being. And this is something, a double layer indicator we need to define first. Because if you look into the methodological equation level, you would see that there are very less definition in terms of how to develop a set of equation to quantify this comfort level of well-being. So this is something, there are some studies done, but still not sophisticated enough to model them into future projection. So that is probably my reflection. I don't know whether Alice you would like to add.
Quickly add. So I'm definitely not a transport expert, but I think it's important to stress that the decent living standards concept always starts from the concept of service provided. So in this case, we have, for instance, PKM, so passenger kilometer as a basic unit for transport service. Then there is a question of technology. So what transport modes are we talking about here? Oh no, this is okay. Yeah. So are we providing those PKMs that are currently missing with cars, or is it public transport instead? And this is, of course, in energy terms, it's very different. Yeah, so I think we need to understand basically what technologies are available and what we can do there. And I would also like to bring here this systemic perspective that we also discussed this morning, because of course, this is a very much important question, especially for the global South. How will the future cities look like in the global south. And here we really need to bring together the different sectors, because if you have a compact city form versus sprawling, this has very different implication for buildings, for transport, and all for it's a completely different world we are talking about. And 50% of the building stock still needs to be built, right? This is what we discussed this morning.
Not to forget remote working versus actually working in place work.
Yeah.
That
Yes.
really affects your
Yes.
demand.
Absolutely.
So definitely digitalization, but also the circular economy, the sharing economy are mega trends that we need also to consider, and could also enable and speed up the transition to a lower energy demand system.
And so regarding Dr. Go's reflection about we probably need to take a market preparation rate while designing a scenario. And in HEB model, we do have a market preparation rate. But saying that, sometimes I question this market preparation rate. And let me tell you why. Because in 2016, when I was looking into Indian cooking demand, and that was enormous. Like it was supposed to be like one of the highest sector, and probably all of us has seen those projections. But then in 2000 end of 16-17 period, when the government actually launched the scheme of PM Yojana, where they actually provide access to clean cooking, now we see that the significant improvement in terms of reduction of energy demand has taking place just due to that government scheme, which none of us has predicted. So this probably kind of a policy dynamic, policies are dynamic, governments are changing, and objectives are shifting. Whereas if we have a model, for example, image, message, or in our case, HEB, which are very, very data intensive, to change it year on year becomes very, very challenging. Like you being a modeler probably also acknowledge it. But of course, saying that we do understand and acknowledge that our model should get reflection of the present policies, at least if not year on year, but at least in few years time, for sure.
Baseline. Baseline has to be very. You have to reproduce the baseline for the policymaker to have confidence.
That's true. That's true. Also, here recently, India has, let's say, updated their GDP methodology based on this similar type of topic. But now it is really getting criticized from economists for different reasons as well. But just to, these are the concern we always need to keep in mind. So, but yeah, probably we all are agreeing here in the room. But is there any final question, comments? If not, then time is almost up. Let me see if we have any final question, comments. If not, then thank you so much for your participation and really amazing questions and insight. And thank you so much, Sophia from CMCC and Beninga from IIASA, for organizing this webinar, and here IIT Delhi for hosting us here in India, and all the participants both in room and joining us online. Thank you so much and have a great rest of the day, and talk to you soon. Bye-bye.